Hi everyone, talk you through the equilibrium constant lab. So how we find an equilibrium constant. This is actually what's on Pivot is actually modified from an in-class assignment, right? So we actually do this lab in person, and when we do this in person, there's lots more experimental tricks and details that aren't covered in the Pivot site. Okay, but other than that, the theory is just the same. So what I'm going to do, I'm going to go through my regular in-semester Prelab, but then just skip the experimental stuff that only applies to meeting on campus. All right. Now, again, the usual things. Finish equilibrium 1 packet before you try this, okay, because you need that essential background of what an equilibrium constant is, okay. Try a little homework, so try and do that Monday or Tuesday of this week, right? Okay, and then then you'll be equipped to come on to this. All right. Now I'm also, and it's actually in the second equilibrium packet, I'm going to show you an introduction to the ICE or ICE method, which is kind of important for subsequent work. But we'll meet it here for the first time, and I'll take a little bit of time going through that with you. Okay. And don't forget, this is due on Friday every week now before 5 p.m. Okay. So just got a blank piece of paper here, right? Okay. So what we're going to do, and I'm just going to kind of cheat a little bit and look over my regular class notes here. So chemical equilibrium, find Kc. And, oh, there we go. So obviously, yeah, we're going to find the equilibrium constant K. It's going to involve solutions with a concentration. So Kc, or just K, right? Remember, they're kind of synonymous. All right. Now the reaction, we're going to take iron plus 3 ions, right? That in its natural state is kind of an almost colorless solution, right? It has kind of a dirty brown tinge to it. And then thiocyanate, or thiocyanide, I should say. Equilibrium with, there's that classic, right? I think actually I looked through your lab, they actually do have a way to insert that now on the Pivot, which is nice, right? So make sure you include that one in your answers, okay? And you make iron SCN, I'll put brackets around it, 2 plus aqueous. So it's a 1-to-1 bump. This thing right here is interesting because that's kind of a red color, right? So you can use absorption spectroscopy, just like we talked about in the last lab, to measure its concentration. Remember, absorption is proportional to concentration, and we use that theory again this time. And should we be in lab, we'd make these solutions. Okay, now remember, an iron complex, which this is, hemoglobin, is what makes your blood red. Okay, so it looks just like blood, which is kind of interesting. Okay, so there's our equilibrium. Okay, therefore K, I'll just skip with the C, right? K equals products. So it's the concentration of FeSCN. And I'm going to put the product, right, 2 plus. And I'm going to put at equilibrium, okay, because that's important to understand that K actually is measured at equilibrium, all right, divided by. And you're asking yourself, well, why is he saying that? It's because when we look at the other variables in this equation and we look at the initial change equilibrium math, we're going to have sometimes a little I subscript, which will mean initial concentration. Obviously, that's not the same as at equilibrium because it changes, right? 2 reactants, so remember we multiply when we add, and the stoichiometric constants are all 1, right? So that makes life a little easier. Equilibrium, SCN minus equilibrium. It's not really necessary to put the aqueous because they're square brackets, but equilibrium, yes. Okay. All right. Yeah, make it consistent. So obviously, when we determine the value of K, right, you need to find all 3 of those variables. You need to find FeSCN, concentration, equilibrium. That's from absorbance, right? Which we'll talk about in more detail in a second, but you've seen it before. You also need to find the Fe3 plus and the SCN equilibrium, and that's done through the ICE math, right? So that's kind of setting you up. So the way into this experiment, as is in many experiments, the way in is often through absorption. If it's a colored material, yeah, we can find its concentration. Once we find the concentration of one, it's mathematically related to the concentrations of the other, so you can do some nice math to find those too. All right, so tricks. So in a lab, this will be more important, okay? Less so here, but it's important to see where this stuff comes from, okay? So, as we mentioned, FeSCN, iron thiocyanate, is red in color, absorbs at 470 nanometers. So it actually absorbs blue light around 470 nanometers, and what's left is red, right? Remember, it's the complementary color you see always. Okay, so should we use our diode spectrometer, much like we did in the last time, we'd shine light at 470 through it because that's where it absorbs, right? Okay, now we need to know the relationship between concentration and absorption. Now remember, concentration of this thing is only proportional to absorption, right? Okay, now absorption itself, remember, is the minus log of the intensity before and after, right? So don't forget that from last time, all right? All right. So I think I asked you to do that in the lab. You have to, you know, it's a little bit more busy work. You have to work out the absorption from the intensity differences, you know, light going in, light going out, minus log of that is absorption, all right? And then that absorption is proportional to concentration. So what we actually do is we draw a line in the sand and we actually work out in lab the absorption for a known concentration, right? So we call it a standard, yeah? So make a standard, all right? And what we do is we put that standard of known concentration, standard known concentration, in the spectrometer, and we record its absorption, right? So whatever the absorption happens to be, maybe it's 0.6 equals 0.002 moles per liter or something, right? And then we know that relationship and we can do some clever math, right? So therefore, then measure A for samples. So you have some samples, you want to find the concentration of this stuff, yeah? And you find the absorption of those samples. Then the clever math, right? Then, here's the fun part, right? I'm going to make sure I get this right. A, the equilibrium is proportional to the concentration of FeSCN 2 plus equilibrium for any sample, right? So this is sample 1, 2, 3, whatever sample you got, right? Okay. But we know A, the standard, is proportional to FeSCN 2 plus standard. Okay. There's the trick, right? So how do you get rid of proportionalities? Well, if there's obviously a constant here, right? Maybe it's, you know, some number, pick a crazy number, 25, right? 25 times 25, 25, and that would be equal maybe, right? But we don't know what that number is, right? But whatever it is, say it's just constant, right? When we divide these out, that constant disappears, it turns to 1, right? So therefore, that is true, okay? We have the absorption of the standard and its concentration, the absorption of the test sample, and we can rearrange this equation to find the concentration of the thiocyanate complex, iron thiocyanate, at equilibrium. Therefore, FeSCN 2 plus equilibrium equals, so bring this over here, right? It's coupled absorption over the standard's absorption times the concentration of the iron standard. Okay, so we know that, we know this, we know this. We can work out the concentration of the product in any equilibrium mixture from this relationship, right? So that's kind of important, man. All right, if you think about it, if you're keeping track here, we need to find these three things, right? Check, we got that one, right? So we can have several equilibrium mixtures, and it doesn't matter what concentration of reactants you start with, K, when it establishes equilibrium, is always going to be the same number, right? Okay, so we can do multiple trials, and K will always be the same. K, remember, is products over reactants. So in each trial, we're able to figure this top one out by using that equation. Fantastic. All right, now, draw a line into that, literally. Right? Now, in the lab, when we did this in lab, it was 0.00020 moles per liter. That was a given, right? So that was given in the lab. It's probably, I didn't check fully, but it's probably also given in the pivot. So just double check that. Okay. Office hour, if it's not, right? Okay. We'll just leave a discussion point. Okay, we'll look at it. All right, now the ICE method, right? ICE stands for initial change equilibrium, yeah? So let's keep our eyes on the ball, right? We now have to find, for each trial, these values, the value of the iron 3 plus reactant and the thiocyanate reactant at equilibrium, right? So they're going to change from their initial values to something at equilibrium. However, key point, we set up the experiment. So even though we change the numbers, we know what those numbers are, right? So we add iron 3 plus and thiocyanate ions to a test tube. They react to form product. Products to reactants also have that fixed ratio defined by K. All right. So the question is, how do we find these? Well, we use this method, ICE method, right? So now, watch this one, right? So this is kind of important. So ICE method. And this will become very important as we go through. Literally any equilibrium math relies on the ICE method. It's just that you kind of modify it slightly for much more challenging things like buffers, right? So later on we'll talk about buffers. Buffers are fundamentally a twist on the ICE method. People get confused with them. They shouldn't. When they break it down to its basics, it's just an ICE grid, right? So what do we got? Well, how do you set it up? So you go Fe3 plus. I'm going to set up the equilibrium, right? There's our equilibrium. I'm just going to set it up. Okay, so that's our equilibrium, right? And then down the side, I for initial, C for change, E for equilibrium, right? Like a grid. I love grids. All right, now, if you think about it, because you're mixing these from two test tubes, right? You set this up, you set the initial concentration. So I'm going to write like it symbolically, and this is why it's important. If you remember that first one I did, I had EQM, right? So if I go back real quick. Concentrations at equilibrium, right? That's when it's finished its reaction, yeah? When we set this thing up, we use the subscript I here for initial, right? So you always know the I value, right? Whatever that concentration is. Maybe it's 0.1 mole per liter or something, whatever it is. It's in the pivot, right? This one then, obviously, SCN minus. Again, a value we know because we mix two solutions together. This guy here, we are going to assign 0 because right at the nanosecond you mix them, they haven't reacted yet, right? So initially, product concentration right at the start is 0. Yeah, it will form as the reaction progresses, but right at the start it's always going to be 0. That's important. All right, now the fun stuff, right? Now I'm going to kind of exaggerate. One of these reacts with one of these to make one of these. We don't know how much out of that, whatever concentration is going to react, but we do know the ratio. 1 reacts with 1 to make 1. I don't know the number. What do you do in math when you don't know the number? X, right? Now, these are reactants, so they're going to disappear. So the change is I'm going to lose some amount X. I don't know that number yet. Figure it out later, right? But hey, that's mathematics, right? 1 reacts with 1 to make 1, so I lose X. I lose the same amount because it's 1 to 1, so X and X as well, right? It's all about stoichiometry. Then I make 1, so it's going to be plus. So that key second line there, the change, it's all about stoichiometry. 1 reacts with 1 to make 1, so I lose X. I also lose X because it's 1 to 1. And I make X because it's 1 to 1 to 1. If there's a 2 there, that would be 2X. In the later examples, it won't be a 1. It might be a 2 here or here, right? So the number of X's is the same as the stoichiometry. Okay. Now, if you think about it, what's the equilibrium? Well, it's my initial amount minus what went away if it's a reactant or it's my initial amount plus what I made as a product, right? Okay, so the equilibrium amount is Fe 3 plus I minus X, and I'll put that in a big bracket like that, okay? So initial amount, some of it reacted away, we don't know what it is yet, so that's what's left. Similar here, SCN initial minus X. Here we made product, right? Started with 0, made stuff, so that's just X. Fantastic. Now, you should get excited about this, right? Because it's algebra, right? If you think about it, if I want to figure out these guys, and if you think about it, what is that? That's just Fe 3 plus that whole thing. Equilibrium, isn't it? That's what we've got to find out for that first equation, yeah? So that there is now, hey, the initial minus the change, right? The other one in the term there it is, right? Oh, sorry, there it is. It's this one. So that's also SCN, oh, too much, oh, minus equilibrium. All right, and this guy, of course, X is what? It's FeSCN equilibrium. We already have that one. If you think about it, we already have that one from our other equation. Okay, so now let's set up K again, right? So K equals, now do a bit of creative origami here, right? Here is my original, right? So I'm just going to repeat that, but now with the variables from the bottom line in the equilibrium, right? So let's do that. Equals, well, FeSCN 2 plus equilibrium. That's from equation 1, right? Okay. Divided by, and then I'm just going to sub, for here, I'm going to sub this. For here, I'm going to sub this, right? And these are now things you know. Fe 3 plus, concentration, initial, you know, right? Minus, oh, yeah, minus X. You know what X is, right? Because you worked it out from this equation. Remember, that's X, right? That's X. Okay. Times SCN initial minus X. Boom, boom. There we are. So you can substitute in the values. This one, just to recap, we got from our absorption data, standard absorption ratio, defined X essentially, right? Once you got X, you know the initial concentrations, so you can find the equilibrium by just subtracting X here. Okay, all right. Hopefully that makes sense, okay? We want to look at that a couple of times, right? So just to recap, right, one more time. I'll go through the whole thing real quick. Okay, so we're finding the value of K for this reaction, yeah? It's products over reactants at equilibrium. That's the key thing, yeah? So we need to find those three things. The first one, the top one's easy because it's colored, yeah? We can use an absorption spectroscopy experiment to find that. Absorption is proportional to concentration, right? However, a little trick then was because, hey, absorption is proportional to concentration. For the standard which we set up, we know this concentration for a standard, we just find its absorption, we stick it in the machine, yeah? And then we find the absorption of the equilibrium mixtures, right? So there might be several mixtures, yeah? And we can find the concentration in there of this guy because, hey, even though it's proportional, divide them out, you get this equation right here, okay? Now remember, we're going to call that X, the equilibrium concentration of product is X in the ICE method we just showed you, right? So if you like to think about it as X or this, it's fine, either one, right? And then there it is, right? So we do our ICE method. We know what this is because we set it up. We know what this is from our experiment. Therefore, we know this guy, we know this guy, and we know this one from the previous absorption. Okay, so you can find the value of K, take an average, and you're good to go. All right. Okay, so try and get this done, in a reasonable amount of time. Try and get it done by Wednesday night. And if there's any kind of last-minute questions, ask me on Thursday morning at the office hour. All right. I just looked out the window. The snow's melting. Might be worth venturing out. We'll see. Okay. See you guys next time.